So this last video is on metabolic rate and temperature regulation in our bodies. So our metabolic rate, remember metabolism is the sum of anabolic and catabolic reactions in the body. So your metabolic rate is that total heat produced by all chemical reactions, whether it's anabolic or catabolic, and mechanical work of the body. So it's a total of all that heat produced in a specific or given period of time. So the way to directly measure it is with a calorimeter, because that's heat that gets liberated into a water chamber. Now that's not very convenient. We're not going to put ourselves in some water chamber. I guess you can, but not a very convenient method to measure metabolic rate, but it would be direct, because remember, a calorie is the energy it takes to raise a certain amount of water 1 degree. We had that definition a while ago of a calorie. So that heat released is a direct measure of your metabolic rate. But it's more, it's indirect, but more convenient way to measure a metabolic rate. Metabolic rate is with a respirometer, measuring oxygen consumption, because it's directly proportional to heat production. So the rate at which we use our oxygen relates to how much work we're doing. And that makes sense, because you're exercising, you need more oxygen. So anytime our body needs to process or build or break down different products and reactions, of course oxygen is needed to do that work. So our basal metabolic rate, our BMR, is the rate, well, we consider it a bare minimum rate, meaning only essential activities to keep you alive. So when our metabolic rate is the absolute lowest, that's your base or basal metabolic rate. So you'd be in a pre-absorptive state, 12-hour fast, laying down, you're relaxed mentally and physically, adequate room temperatures. It's measured in kilocalories per meter square per hour, meter square of your body surface area. So in a regular or average size adult, BMR works out to be 66. Here's what influences BMR. Age decreases it. Males increase BMR compared to females. Muscle mass will increase BMR. So someone who works out with weights or athletes usually have a higher basal metabolic rate because of the work or the heat produced by muscles as they're being used. Body temperature, BMR increases with temperature. Stress also increases BMR. Thyroxine, produced by the thyroid gland, increases with oxygen consumption. Heat production, ATP use in cellular respiration. So therefore, BMR increases with thyroxine, which is controls your metabolism in your body. So it makes sense. Higher metabolism, higher metabolic rate, well, more thyroxine. And someone's producing too much thyroxine, that would be called hyperthyroidism. That would just make sense. Hyper means excessive, thyroid hormone, a high basal metabolic rate. And we've seen this in the past, where your body is going to start breaking down fats, breaking down proteins in your tissues. So even though you're hungry all the time and you're eating a lot, you'd still lose weight with the hyperthyroidism. Breaking down proteins in bones can weaken them, and in muscles, including the heart, tissue can begin to atrophy with hyperthyroidism because of the demands to metabolize. Hypothyroidism, not enough thyroxine, decreases metabolism, so therefore it will decrease your basal metabolic rate. And the result, well, nutrients will start building up because they're not getting broken down. So obesity and even your thought processes will slow down with a low metabolism. So your total metabolic rate depends on your activity level. So rate of kilocalorie consumption to fuel all your ongoing activities. So if you're exercising, well, your TMR will be much higher. If you're just walking, let's say, it'll be much lower than exercising, but higher than basal metabolic rate if you're doing at least something. So it increases with skeletal muscle activity and, of course, with food ingestion, because the process of digestion, absorption, and breaking down food into nutrients produces heat. And that's called food-induced thermogenesis. Thermo meaning heat. And what's creating the most amount of heat is with protein ingestion and alcohol ingestion. Here's our normal body temperature, 35.8 to 38.2, of course in Fahrenheit, 96 to 101. Sometimes that varies slightly from individual to individual. And this is our normal body temperature because that's where enzymes work the best. That's their optimum temperature range that our enzymes can perform all the functions that they perform in our bodies. If our temperature increases above normal, we would call that a fever, of course. Now the proteins, which of course enzymes are proteins as well, they start to denature or unwind or unfold, and that will depress neurons as well. So our body activities will decrease when our temperature gets above our normal range, or at least the proteins in neurons can't work as effectively. In children under 5, a temperature of 106 can lead to convulsions, and 109 is the limit of life. Now, if we go under our normal body temperature, that's not as bad. We can tolerate that much more because the proteins or enzymes, even though, well, they are working at a slower rate at colder temperatures, they are not denaturing. So higher temperatures actually unfolds them, rendering them useless, whereas lower temperatures slow them down. So that's not as dangerous. And when we're talking about those temperature ranges on the previous slide, that has to do with core temperature, not shell. And here's the difference. The core temperature is the temperature around your organs in your body cavities. So like your cranial cavity organs, your thoracic and abdominal cavity organs, that's where the highest temperatures are in our body, in the core. It's pretty constant, so even though the temperature outside of our body can change very drastically, the temperature in our core remains fairly constant within that normal range that we saw. Blood is the major agent of heat exchange between core and the shell, which is your skin. That has the lowest temperatures. It can fluctuate tremendously, 20 degrees Celsius or almost 40 degrees Fahrenheit, depending on the environment that you're in and your heat production. So we've seen this before, but it's relevant now, so let's do this again. We have homeostasis of body temperature, but when it drops, it activates our thermostat in our hypothalamus, which goes to two areas. We want to get warmer to create a balance again, so it will activate our skeletal muscles to shiver in order to produce heat, because muscle contraction produces heat, thereby raising the body temperature. And it will go to the blood vessels in the dermis of our skin, which causes them to contract. So this shell blood, or body temperature, well, that blood which carries heat will get diverted, right there, to the core of your body, so less heat will be released, or less heat will radiate through your skin, thereby preserving the heat in the blood, which acts to raise your core temperature, bringing our homeostasis of body temperature back to normal. So during very cold weather, blood flow, like we just saw, from the skin is restricted, it's shunted to the core, and that's fine if it's for brief periods of time, but if you're outside too long, they can actually form ice crystals around the cells, around your blood, causing them to die, and that's dangerous. That's called frostbite, and which could result in vast dead tissue if frostbite persists. So just the opposite here. Our body temperature, when it rises, well, that stimulates the heat loss center in our thermostat of our brain and our hypothalamus. That's going to go to blood vessels in our dermis and tell them to dilate. So when these blood vessels dilate, now more blood from the core enters the shell, and that heat from our blood, which is near the surface of our skin, will radiate into the atmosphere, thereby cooling you down, releasing heat from your body. At the same time, sweat glands will release perspiration onto the surface of your skin. That doesn't cool you off, actually, but it's when that sweat or perspiration evaporates from your body that it pulls heat away from our body. And so in a humid environment, we can't do that very well because there's too much moisture in the air, so we still feel uncomfortable if we are sweating and it's humid outside. But in a dry environment, it could be just as warm, but you feel more comfortable because that sweat's allowed to evaporate from the body. So both mechanisms here will decrease our body temperature to maintain homeostasis of normal body temperature. So here's a dangerous situation, hyperthermia, hyperexcessive thermia temperature. So elevated body temperature depresses our thermostat and our hypothalamus. So this is overexposure to hot and humid environment. So recall what happens in our skin with a hot environment and the perspiration needing to evaporate, which can't do it very well in the humid environment. So a positive feedback mechanism, which we call heat stroke, very dangerous, begins at 105 degrees core temperature. And positive feedback, remember, is usually bad, and it is bad in this situation, because with a depressed hypothalamus and the heat loss mechanism being non-functional, meaning your blood vessels and your dermis won't dilate, you're actually not going to sweat because of the heat loss mechanisms being non-functional. So the positive feedback is, because of these increased temperatures, we know higher temperatures cause a higher metabolic rate. And what happens as a result of more metabolism? More metabolism, more heat. More heat, more metabolism. So body temperature just keeps raising, keeps going up and up and up, and that's heat stroke. And we can kind of see where we're going and how dangerous that is. So the skin is actually hot and dry because we're not perspiring with the non-functional mechanisms. Organs can damage. The brain can damage. It's fatal if it's not corrected immediately. And correction needs to be to immerse the person in cold water and obviously give them some water as well. So heat exhaustion, not as bad, but could get worse, could become heat stroke. But heat exhaustion, another term for it, exertion-induced heat exhaustion. So this is vigorous, results from vigorous exercise in the heat and humidity. And if the person's not taking in enough fluid, they can become dehydrated. Also, of course, excessive sweating because of the heat humidity will cause that dehydration as well. So if we're losing fluid, consequently our blood pressure will lower. And if your blood pressure gets too low, your body responds by fainting or collapsing or fainting. And if you collapse, well, that's your body's way of delivering blood to the brain under low blood pressure. So the heat loss mechanisms are still functional, so they're still sweating. Skin is going to be wet as opposed to heat stroke, which is hot and dry. This could progress to heat stroke if the body's not cooled. And here are the key points to hypothermia, which is the opposite, hypodeficient heat. This is low body temperature from cold exposure. Vital signs will decrease because cold slows metabolic processes. start to feel drowsy, and actually a comfort sets in because of the slow metabolism, very slow metabolic rate in the body. Shivering will actually stop at 30 to 32 Celsius or 87 to 90 Fahrenheit. And this, if not corrected, can progress to very dangerous things like you can read here. And finally, fever. Controlled hyperthermia. So fever is by design because your body may have an infection. It could be cancer or allergies or central nervous system injuries. So in any of these circumstances, our macrophages will release cytokines, which we've heard of, called pyrogens, pyro meaning fire, and they act on the hypothalamus. So they say, well, instead of 98, 99 being normal, let's raise that to 102. So now our thermostat is set differently. So our body believes that, for example, 102 is our new normal for temperature, core temperature. So that is in response to try to fight these things up here. So that triggers heat-producing mechanisms, shivering, temperature rises, of course. So our natural body defenses, or our antibiotics, reverse disease processes. So it's basically this heat is giving the advantage to our immune system, which will fight more effectively and typically disadvantages the pathogen. So resets thermostat to lower normal level, activating heat lock mechanisms. So when the infection has been fought and your fever is over, well, your thermostat in your hypothalamus returns to normal, and that's when they say the fever's broken, and all of a sudden you start sweating. Because during a fever, even though you're warmer than you normally are, you still shiver. Shivering usually is a result of cold, and that's because your skin is warm, and the contrast of the cool air makes it feel cold, and you start shivering. But the shivering occurs to raise your body temperature as well, because the hypothalamus reset the thermostat to a higher level. So shivering will get it to that higher level because of the heat produced from muscle contractions. So when the thermostat brings the level back to normal of body temperature, and your fever is broken and the sweating starts and shivering stops, now that temperature could fall back to a normal level.